basically, if we take the same capacity formula here, right? And when this number is also a random number, we are going to do integration of this thing over the distribution of the random variable. And when you do that, you are going to end up with the sizer channel like this. The performance of the sizer channel will come to this because of the random variable nature of the channel coefficient H1. So now, so here also the capacity will be a random number if it is a sizer channel. Here also the random number, but it has a better, much better distribution compared to the sizer. You can see that this is the sizer and this is 4/4. Much better distribution. And that is what we are looking at, right? So the P is nothing but the power loading or power used for transmitting in each chain. And we can do that some manipulation, and then you can get this P matrix out. Anyway, this equivalent. Let me not go into the math now, but I just want to have an intuitive feel for how this whole thing works. Call Purnama.
Yeah.
So this channel matrix can be decomposed into singular value decomposition, SVD. We'll see that why that is required in trying to understand what capacity you can get, what advantages you can get. Okay. So now let's look at, well, this is simulation result. Yes. How does it work in practice? Okay. In practice also, it is measured and matched that we are indeed getting these exactly similar distributions. Okay. Here is what is shown is both are simulation only, but a different type of simulation. But you can actually find out in practice also it comes very close to this. The actual measurement in real field measurements. So actually both helps us. Basically the more number of transmit antennas in the receiver and transmitter both indeed help us in achieving what we are getting this, right? There's one more thing I want to highlight. Okay, fine, let's move on now. So, okay, how does that help us in 5G, right? Or what does it mean to 5G? At large number of dimensions, that means more large number of NT and NR. Although in practice you can see only 8 seems to be enough, but we can take that as a large number. Okay. There are guaranteed that there will be at least some channels have good SNR, for more than 99% of the time. See, since it's a random number, we can never say 100%. We can say this number 99 or 90 or 80. Accordingly, the rate will be different, or the SNR will be different. But it is guaranteed that some channels will have good SNR, and that is enough for us to do the Mimo communication. Okay. And we can, what does that mean? We can bound the rank of the matrix. The channel matrix H as the rank of H is guaranteed to be more than, let's say, 4 90% of the time, right? For a 8 by 8 case, I'm just picking a number. That means I can do simultaneous transmission to 4 users. Okay, channel rank is 4. I have 4 independent vectors. I can use that to talk to 4 users simultaneously. What does that mean? Going back to this resource allocation, when you come to this particular user, let's say this user, if the SNR is good, I can put 4 users here instead of 1. I can put another 4 users here instead of 1. And similarly for the MMTC, I can pack more number of users here. That is the benefit that we are going to get. Okay. So large array means that capacity can scale linearly, right? Okay, just to be precise, the capacity scales linearly as minimum of NT, NR. Okay. What does that mean? Even if I have 12 antennas at the transmitter, at the base station, and the mobile has only 2 antennas, I cannot increase the capacity more than twice. The capacity will go as a minimum of NTNR. Okay. However, it scales. It scales linearly. It scales linearly with the array size. Okay. So now let us see. We saw what Mimo channel can give us theoretically. We also kind of match the PDF and CDF in practice. And let's see how we can now use that multiple rank in the channel matrix, right? These are the typical coding techniques used for, there are 2 words. One is for diversity. Other one is called multiplexing gain. You should remember these 2 words. This basically tells how many parallel users I can transmit using same frequency and time resources. That is multiplexing gain. Okay. Diversity is how robust or reliable is my connection. This tells you what is the bit error rate I can get. This tells you what is the maximum data rate I can get. This tells maximum rate. This is minimum rate and minimum bit error rate. Okay. This will be maximum rate, moderate bit error rate. Okay, so we'll see how the coding, what we do as Mimo coding, right, is different type 1, type 2. For these 2, we do different coding techniques. Okay, we'll see an example for both of them. And pre-coding, this is particular coding is called pre-coding. Why it is called pre-coding is, if X is the signal I want to transmit, it can be QPSK or QAM or any symbol, right? Signal or symbol I want to transmit. And N is the receiver noise matrix. Okay. And P is a precoding matrix which converts this vector into another vector, or this matrix into another matrix, or in other words, this is a linear transformation, mathematically speaking. Linear transformation, what you read in linear algebra. Linear transformation before it is sent to the channel. After channel, this is a received signal. Matrix or vector, depending on whether this is a vector or matrix. If the signal is a vector, you'll get a vector. If it is a matrix, you'll get a matrix. Right? So since we pre-multiply the symbols before it is sent to the channel, this is called precoding. This is called precoding matrix. We code it before sending to the channel. Okay. We can pre-code it for high data rate or single user Mimo. That means one user gets all parallel channels. That means the user also has multiple antenna. That is minimum required. If he wants 4 channels, he should have minimum 4 antennas. Or we can use a pre-coding for talking to multiple users same time. Here, one user gets 1 channel, multiple users occupy all spatial channels. Okay, so you can do coding for this, you can do coding for this, or you can even do coding for higher rate or diversity. The multiple ways you can do the coding. Let's see example for one of them in each case. Let's say we want to do the pre-coding for maximum data rate or maximum users simultaneously. So how we are going to do that is, let's look at the singular value decomposition of the channel matrix H. So you have the singular values followed by right singular vectors and left singular vectors. Now use the right singular vectors or the columns, a few of them. Let's say M columns. Why M columns? If the channel rank or the rank of H is more than M, more than or equal to M, greater than or equal to M, I use M columns of V as a precoding matrix. Once I multiply the signal with the V, basically P has become V, P equal to V here, right? I precode the signal with the precoding matrix V. What happens when you multiply with H? This V Hermitian V goes to identity because orthonormal matrix. The effective channel reduces to this. Now in the receiver, you pre-multiply this with the U Hermitian here. Once you do with the U Hermitian U, that also goes to identity. You get this only the diagonal matrix. Sigma is a S singular values. Okay. So what we have done is we have converted a Mimo channel into parallel CISO channels with no interference among them. That's the key. So when I am transmitting in a Mimo channel here, see, one user's transmission is going to be simultaneously received by all, and this K can interfere here, right? Now this interference is practically removed by this particular coding. It's called spatial multiplexing mode. I have removed all interference between the various channels, so I can allocate each channel for one user, or I can allocate all channels for one user. Accordingly, now since I have m channels here, my data rate is m times the channel data rate for one link. So I have increased my throughput m times. M times higher throughput. So that is what we are getting by this code, doing the coding. So all that we have to do is take the singular vector of right singular vector of the channel matrix and use that as a precoding matrix in the transmitter, and use U Hermitian as a precoding matrix at the receiver. Sorry, you can call it as a post-coding matrix. This is precoding, this is post-coding. Any doubts so far? This is complex math. I want you to understand. So you are going to write Matlab code again, same way what I mentioned. Matlab live editor mode. It will save the file as .mlx. You have to generate two files, one for transmit, one for receive. .mlx. Okay. So you take 1000 QPSK symbols, and as I given one example, you can do it multiple way. You can generate a random symbol number and map it to a QPSK constellation point. And I want the constellation to be unit energy. That means the QPSK constellation, this energy is 1. That means you are going to have 0.707, j, 0.707 here. And similarly, the other constellation points are same unit distance away. Okay. So these are the 4 constellation points for the QPSK, and they all have unit energy. Okay, so this you can take it as 1 by square root 2 if you want to be precise. And now what you do is generate 2 complex coefficients with 0 mean. It has to be complex, remember that. 0 mean and unit variance. And these are the 2 channel coefficients, H1i, H2i, what I mentioned in that previous slide. Now take any 2 symbols randomly, x1, x2, from these 1000 symbols. Let's say first 2, right? And now you create the output for the channel output. Channel output, which is basically y1i, y2i. This is what I need. Now add noise with some SNR. You can use the AWGN function for that. And this is assignment number 1. So basically, you are going to plot y1i and y2i as a constellation plot. What is Constellation Plot? We are going to plot real here and imaginary here. Okay, with a circle or a cross as the characters. So you are going to get some plot, something like that, scattered plot. Since it is noisy, you will get all kind of fuzzy cloud around the constellation point. Okay, you will not be able to make out QPSK constellation from that. That's the whole idea. The constellation plot is going to be like this. Now the part 2, you are going to do the decoder. I have given the expression for x1 hat and x2 hat. So you need to get x1 hat and x2 hat for every pair that you transmitted. Okay, after decoding, you check the error whether it is correctly received or not. Because you know the original symbols what was transmitted. Now we repeat this for every pair, and then you compute a symbol error rate over 1000 symbols. Now repeat this over 1000 experiments for each SNR, and I want the plot SNR versus symbol error rate. Like that, some plots will come. Okay. Why I have put 2 is this is for 2tx, 1rx. Another one I want is 2tx, 2rx. Okay, and I'm not going to give you idea about how you are going to extend it for more than one antenna. Think about it yourself. It's very easy. Now this is the example plot that what you will get. This is not exactly same. This is what I have done is bit error rate, but you will get symbol error rate similar to that. So you will get one plot like this, 2x1 allometry, and another plot like this, 2x2 allometry. So basically you are going to see this and this in your plot. Very similar looking plot you will get. Not exactly same. Because this y-axis will be different for symbol error rate. Symbol error rate scale will be different. So you will get similar plot, but the y-axis will be different. And I have done for, so you can see from SNR 4 dB to roughly, let's say 14 dB I have done. You can do that in 1 dB steps. Okay, let me correct it here. 4 dB to 14 dB in 1 dB steps. And submit the Matlab code as MLX files, what I mentioned here.